Today we're going to be looking at special right triangles again. Today we're going to look at a different sort of right triangle. So we're going to look at what's known as the 30, 60, 90 triangle. As the name would suggest, our triangle will look something like this. We'll have a 90-degree angle in there, obviously. We'll have a 30-degree angle in there. And then, of course, because we have to add up to 180, our final angle is 60 degrees. So this is the type of triangles that we'll be using. And again, we'll be using special right triangles to help us kind of get away from the Pythagorean theorem and use other means of finding what we need, whether it be certain side lengths or even certain angle measures. That way we're not relying on Pythagorean theorem all the time. So let's take a look. This particular triangle can be developed from an equilateral. So take a look. I've got just drawn a nice equilateral triangle here. And what I'm going to do is I'm going to divide it with an altitude. Cool. So that gives me 90 degrees on that side. We know that this is 60 degrees because it's an equilateral triangle. And then, of course, because of our triangle sum theorem, we know that this is 30 degrees. So there's our 30, 60, 90 triangle. So let's look at the side lengths here and see if we can't come up with some sort of relationship. So here's my triangle, and I'm going to ignore this half, so we'll just pretend like it's not there. I'm going to call this the short side. All right, and I'm going to call it the short side because it is indeed the shortest side. Notice it's opposite the smallest angle. So I'm just going to call it side X. And the reason I'm going to give it that is we don't know what the value is, and we want it to be true for any 30, 60, 90 triangle, not just this one. If this side is X, well, then that means this side has to be 2X. And here's how I know that. Notice our altitude comes down. It's a right angle. Notice I've got a point here on my altitude. So that means these two sides have to be the same. Notice we've got that perpendicular bisector going on. And since it is a perpendicular bisector, that means this other side would be X. So I've got X here, that's a grand total of 2X. And since it's equilateral, this side and this side have to be the same. So cool, and I'm going to mark that out just so it doesn't confuse us. So I've got my short side, we'll call X. We've got our hypotenuse, so it's worth twice as much, so 2X. And then I've got this final side here that I'm not sure what it is worth. And we're going to call it the other side. Obviously, it would be the other leg measure. So we've got the short side, we'll call it the hypotenuse, and then this other side. So let's use Pythagorean theorem, and we'll see if we can't figure out what it's worth. And I'm just going to use a question mark to represent its value at this point. That way we don't get another letter or variable in there. So again, Pythagorean theorem to start, and then we'll see if we can't work around it. So in this case, I'll have x squared added to our unknown squared. And that's going to equal 2x all squared. Now notice I do need to use parentheses here. I can't write it like this. If I wrote it this way, the 2 here for our exponent would only apply to the x and not to the 2 as well. Notice I've got to square everything, so that's why we're using parentheses. Well, let's work this out real quick. So we'll have x squared added to our unknown squared is going to be, let's see, 2 squared is 4, x squared is x. Cool. So that's what we've got. The next thing we're going to do is go ahead and subtract an x squared from both sides. So if I have 4 of them here and 1 of them there and I subtract, I will find that my unknown squared is 3x squared. All right, so we're almost there. But notice I want to know what this unknown is all by itself, not the unknown squared. So let's keep working. To get rid of that power of 2, we'll use an exponent. So here we go, use that exponent. Our unknown, excellent, that's what we were going for, is equal to, well, I noticed that this is a perfect square number. X squared is perfect, so we'll go ahead and take the square root of that. So the square root of x squared is just x. And I noticed that 3 is all that's left. Well, 3 is not a perfect square number, so we're just going to write that down, square root of 3. So our unknown value here, okay, is not really unknown anymore. It's whatever x is multiplied by radical 3. So this is our shortcut. This is our way of working around all of this without having to use Pythagorean theorem. So my short side, or that smaller leg, is x. The hypotenuse is twice as much, so 2x. And then what we'll call this other side, right, this other leg, is simply the short side, x, multiplied by radical 3. And for the most part, we'll try to keep radical 3 in our work or in our answers just because it's exact. I don't want to have to sit there and start, let's see, where did I put it? There it is. I don't want to have to sit here and start messing around with my calculator, punching in things like square root of 3 and dealing with that terrible irrational number in a decimal format. That's horrible. So we're going to try as best we can to keep it in that format just to make our lives easier. So, theorem time. Take a look. Just as we said before, in a 30, 60, 90 triangle, the length of our hypotenuse obviously is twice as long as that short leg, so we'll call it the short side. And then, of course, this other side is whatever our short side is multiplied by radical 3. And notice in this case, they swapped the variable out on us. Instead of x's, they used n's. Variable doesn't matter. It's going to work out regardless. So our short side is just the unit, whatever it is. Our hypotenuse is twice as much. And then our other side is the square root of 3 times as much. So we'll use that as we work today. Now, just a quick reminder for our other special right triangle. That was with a 45, 45, 90 triangle. And remember, in that case, we had x's for the legs. And then our hypotenuse was x radical 2. So just keep that in mind. With 30, 60, 90, triangles, we have the radical 3. With 45, 45, 90, it's a radical 2. So try to keep those two ideas separate as best you can. So let's try a couple. Let's see what we can do. So here's our first example. We've got a diagram that we'll use for both of these. So again, one of these is not connected to the other. So we'll do problem 18 here that I found out of a textbook. So we're asked to find, in this case, CE. And that should be a Y. I guess it got cut off there in the photocopy. So CE is this distance here. And then Y, of course, is this distance here. And I'm going to switch out for a pencil. That way I can erase this as I go. And hopefully it'll show up in the camera, okay? We're told that side A, so this side over here, is 10 radical 3. So I'm going to use that to start, and we'll see what we can do. All right. Well, the first thing I need to figure out is CE. So this distance here. So I'm going to pretend like the rest of this triangle just does not exist. Well, notice I've got a right triangle here. I've got 60 degrees. Then, of course, this little bit here would have to be 30. So this is the hypotenuse. Notice it's opposite that right angle. So this is our hypotenuse. I can figure out x by simply dividing this by 2, right? Remember, it takes x times 2 to get this amount. So I'm just going to divide by 2. So x in this case is 5 radical 3. Again, I just divided by 2. CE, notice, is that other side. Notice it's opposite that 60-degree angle. So that's that other side. And we said in order to take the short side to get to this other, we would just multiply it by radical 3. All right, well, radical 3 multiplied by radical 3 is 3. So this other side, this CE in this case, is 5 times 3 or 15 units, whatever we're measuring in, whether it's inches, miles, we don't care. All right, well, let's keep looking. So we know that x, for example, is this 5 radical 3. So I'm going to leave that there for the time being. There we go. And we know that CE, we said, is 15. So let's write that in, 15. That way we've got our measurements going. And then we are asked to find Y. Well, I notice we've got another right triangle here, in this case, CEA. So I'm going to ignore everything over here for the time being, just to focus on this right triangle. Here's my short side. Notice it's opposite the 30-degree angle, so 15 is the short side. And Y, in this case from E to A, is that other measure. So all I have to do is take this and multiply it by radical 3. So Y is just 15 multiplied by radical 3, or just 15 radical 3. There's no need to simplify here. There's no need to approximate. In this case, it'd just be a lot easier and more exact to write our answer as 15 radical 3. Right? So there's that example. Now I'm going to erase these because notice the measurements here are changed out. So I don't want to confuse myself. Same diagram, but new measurements. So let's erase those real quick. And we'll start again. All right? So let's see here. For this one, x is 7 radical 3. So let's make that mark 7 radical 3. Excellent. And in this case, we're asked to find A, CE, Y, and B. Goodness gracious. All right. So let's see what we can figure out. Since we already know x, let's focus on this smaller triangle to start. I think that's just going to make our lives easier. Well, I notice x is the short side. Notice it's opposite that 30-degree angle. So that means A is the hypotenuse. It's opposite the right angle. So this is twice as much. So A is 2 times, let's multiply it here, 2 times 7 radical 3. So 2 times 7 is 14. So A is 14 radical 3. So let's write that in. 14 radical 3. Excellent. All right. Next, let's go ahead and find CE since we're here. Remember, CE is that other side. Notice it's opposite that 60-degree angle. So to take this short side, all I got to do is multiply it by radical 3, and that'll get me this, what we're calling the other side. Well, radical 3 times radical 3 is, not 9. Oh, that's 3 times 3. This is radical 3 times radical 3. So that's just 3. And then we'll multiply by 7. So CE is 21. 21. Excellent. All right, so let's erase those. We don't want to confuse ourselves. Let's see what we got to find next. Next is y. So what I'm going to do is I'm going to ignore the smaller triangle, pretend like it's not here. Notice 21 is opposite 30 degrees. So this is the short side. Y would be opposite that 60 then. So y is that other side. So all I got to do is take 21 and multiply it by radical 3, and that'll give me that side for y. So 21 radical 3. And then the last thing we were asked to find is b. Well, b is the hypotenuse in this case. So if c to e is 21, the short side, all I have to do is double it. So 2 times 21, or in this case, 42. And we're done. So notice, using special right triangles is a lot easier. I'm not having to do all of this a squared added to b squared equals c squared nonsense. I just have to use the relationships that I know to find those problems, and I can do it very, very quickly. Nothing wrong with Pythagorean theorem. It should always be your first sort of line of defense. But if you ever see a special right triangle, then defer to it if you can, just simply because it'll save you a little time and a little energy. Again, nothing wrong with Pythagorean theorem. In some of these cases, once we know two sides, we could use Pythagorean theorem to work it out. In some cases, you won't have near enough information to use it, so special right triangles is where you'll have to go. All right, let's try some others. All right. For example, all right, so let's take a look at our next example. Notice in this case, we don't have enough information to use Pythagorean theorem. We've only got the one side. Since we know it's a right triangle, and we've got 60 degrees here, we know this would have to be 30. This is one of our special right triangles, 30, 60, 90. So we're not going to be able to use Pythagorean theorem. We have to use what we know about special right triangles. So we're asked to find AC, so this is the side we're unsure about. I noticed that the side they gave me is opposite the right angle, so this is the hypotenuse, it's 14. That means the short side is 7. Remember, I'd take 7 times 2 to get back, so to go the other direction, we divide. To find this side, all we've got to do is multiply by radical 3. So in this case, AC is equal to 7 radical 3. Whoa, really out of focus there. There we go. 7 radical 3, and we're done. So again, special right triangles make this a lot easier, and in this case, it even makes the problem possible. All right? So let's try another one. Notice in this case, they've come right out and told us what we have. We've got a couple of different problems here. So let's number them. For some reason, the numbering didn't show up. We'll call this problem 1 and problem 2. So let's start with problem 1. Seems like a good place to start. It says C is 8. So let's write that in. So our hypotenuse in this case is 8. We need to find A and B. So for problem 1, we're going to find A, and we're going to find B. Okay. Well, I noticed that, again, C is the hypotenuse, which means A, in this case, across from the 30, is the short side. So we just divide by 2. So this is 4. B is opposite the 60, so it's that other side. So I'm going to take 4, multiply it by radical 3, and that's just 4 radical 3. No real big deal. And again, go ahead and leave that radical. There's no sense in typing it in a calculator unless you're asked to round. If you're asked to round to the hundredths or tenths or whatever, then obviously you'd have to. But in this case, it's just a lot easier to leave it alone. All right, well, let's try number 2. Let's erase these. We'll use the same diagram, but not the same measurements. So we'll do that real quick. B in this case is 18. Oop, 18, not 16. There we go. And we got to find A and C. Now, I like this problem because it's going to force us to go in the other direction. Notice we've got this other side to start with, And now we've got to go back. So remember, we said our other side is equal to, so in this case, 18 is equal to x multiplied by radical 3. Well, we saw a similar problem like this when we did our other special right triangles. Let's see if we can find a pattern, so that way we don't have to do all the work that we're about to do here every single time. All right. So first thing I'm going to do is divide by radical 3. So let's do that first. So divide by radical 3, divide by radical 3. So I've got x is equal to 18 over radical 3. But remember, we cannot leave radicals in the denominator, so we need to rationalize it. So what I'm going to do to fix this problem is I'm going to multiply both numerator and denominator by radical 3. In other words, radical 3 over radical 3 is a fancy way of talking about 1. And we can multiply things by 1 without really altering the value. So the first thing I'll do is 18 times radical 3. So that's just 18 radical 3. And then radical 3 times radical 3, of course, is 3. And then to finish this off, we need to simplify. Well, 18 divided by 3 is 6. And then, of course, radical 3 would just hang on. So x in this case, our unknown, is 6 radical 3. And that would be our a position. Remember, we were going back to that short side. So 6 radical 3. So how could we go from this to that without all of this nonsense in between? Well, one thing I noticed that we did is that we simply tacked a square root of 3 on, right? Started here, ended here. Cool. The other thing I noticed is that we ended up dividing the 18 by 3. So kind of like our other special right triangle, which in this case, if it was the other form of the special right triangle, it would have been 18 over radical 2 equals x radical 2, right? It would have started like this. And we said, well, instead of doing all that work, for the other type of right triangle, we would just take this divide by 2, 9, and then tack the radical 2 onto the end. That was our shortcut. Notice here it works a little differently. Here, instead of dividing by 2, we're going to divide by 3. So that's our shortcut. We divide by 3, and then we just tack that radical 3 on. So if this number was, say, 21, well, I'd divide by 3, so that'd be 7, and then just tack on the radical 3. So in this case, A is 6 radical 3. Excellent. The other part we need to find, of course, is C. That's our hypotenuse. And we have to double this amount. This is the short side, so we double it for the hypotenuse. 6 multiplied by 2 is, of course, 12. So 12 radical 3. And again, don't bother changing that to a decimal unless you absolutely have to. In this case, we're not asked around, so it makes more sense just to leave it alone. All right. So what we're dealing with today is just more special right triangles. The only difference is the type. Make certain, guys and gals, that you try to keep these two ideas separate. The 30, 60, 90 right triangles are very different than our 45, 45, 90 triangles. If you need help or have any questions, make sure you bring those ideas with you to class, and we'll see you then. Have a good day.